Good morning, everybody. Welcome back to the theory of stellar pulsations. In yesterday's lecture, we have dealt with non-radial adiabatic pulsations, and finally, we have done a local analysis for these perturbations, and we arrived at the local dispersion relation for non-radial adiabatic waves. Local dispersion relation means it is a relation between the wave number k and the frequency sigma. In the local analysis, the coefficients of the differential equations are formally kept constant. So this dispersion relation is a function also of the radius and the parameters of the system, which is essentially the harmonic degree of the perturbation. We have defined two frequencies appearing in this dispersion relation, which is the Brunt Vaisala frequency given by minus gravity times the quantity A. We have seen that the quantity A is essentially the gradient of the entropy within the star. The second frequency is the Lamb frequency, which is essentially given by the sound speed squared. Okay, these are the quantities which appear in this relation, and now we would like to interpret this local dispersion relation and see what this dispersion relation offers as physical insights about the waves traveling, the non-radial waves traveling in our star. Okay, so to identify the various terms or the various waves which are contained in this dispersion relation, we require first the Brunt Vaisala frequency to vanish. So we set A equal to 0 and look what will happen to our dispersion relation. It becomes simpler, and once we do this, put GA equal to 0, then we are left with k squared, and this dispersion relation reduces to k squared, is given by sigma squared, essentially minus the Lamb frequency squared, times 1 over the sound speed squared. What does it mean for the character of our perturbations? Well, if k squared is positive, then we have a so-called oscillatory behavior. Then we have traveling waves or oscillatory waves. Once k squared is negative, then we have exponential behavior in terms of the dependence on radial coordinate. Then we have a so-called evanescent behavior. Then the waves will no longer be allowed to travel, but they decay exponentially. This is the case for this type of waves once the oscillatory behavior is present. For this type of waves, once sigma squared is essentially bigger than the Lamb frequency squared. What is the character of these waves? In order to see that, we solve it simply for sigma squared. So we solve this equation for sigma squared, and we obtain that sigma squared is given by sound speed squared times the wave number squared. The wave numbers are composed now by both the azimuthal wave number, which is nothing but the harmonic degree of our perturbation, and the radial wave number squared, which is k squared. So this is, as you see, sound speed plays a role, wave number, sound speed, and the frequency are related. So this is the dispersion relation for sound waves, and this means this dispersion relation describes the p mode. Now we would like to exclude these sound waves from the general dispersion relation. This is done by requiring that the sound speed goes to infinity. So 1 over the sound speed squared is set to 0. If we do this in the general dispersion relation, where is the mouse? Okay, so we take this dispersion relation and set 1 over the sound speed equal to 0, and then we are left with the following dispersion relation. If we do this, then we are left with a dispersion relation including the Brunt Vaisala frequency and the frequency. So k squared is n squared minus the frequency of our the frequency, and times the azimuthal wave number squared. Well, this means for the behavior, evanescent or oscillator behavior, this means these waves are oscillatory once the frequency stays below the Brunt Vaisala frequency. So in that case, they are oscillatory. If the frequency is bigger than the Brunt Vaisala frequency, then these waves become evanescent. So for an oscillatory behavior, the frequency has to be smaller than the Brunt Vaisala frequency. Otherwise, these waves are evanescent. It's just the opposite to the sound waves. For the sound waves to become oscillatory, the frequency has to lie above the Lamb frequency. Here, for the G mode, for this type of modes, we have that the frequency has to be below some limiting frequency, which is the Brunt Vaisala frequency. Now we do the same as above. We solve this dispersion relation for sigma squared, and we are left with then the following dispersion relation: omega squared, where omega squared is simply sigma squared times 4 pi g mean density. This is done, or this transformation is done in order to get the usual formulation. The standard formulation, we obtain then that omega squared, the frequency squared, is given by the Brunt Vaisala frequency squared divided by the ratio of the radial and the azimuthal wave numbers. So this is the typical dispersion relation of gravity waves. So our dispersion relation both describes the sound waves and the gravity waves together. And by either asking for zero entropy gradient or by infinite sound speed, we can extract them in pure form from the general dispersion relation. Okay, now let's consider this last dispersion relation for the gravity waves. Well, if n squared, which is given by minus gravity times the quantity A times essentially the entropy gradient, if n squared is smaller than 0, then obviously omega squared is also smaller than 0. I will remind you, in the adiabatic case, the omega squared has to be real because the adiabatic perturbation problem is self-adjoint. So the instability can arise in the adiabatic approximation only through negative values of omega squared. In that case, we have an exponential, a purely exponential non-oscillatory instability, whereas stability is characterized with a positive omega squared. In this case, we have neutrally stable oscillating modes. So what we see here, if n squared is negative, then omega squared becomes negative, and we have an instability for n squared smaller than 0, and we have stability omega squared bigger than 0 for n squared bigger than 0. Okay, well, this we have found now an instability with respect to non-radial perturbations, and of course we would like to know what is the physics of this instability, and could it be somehow be correlated or related to the instability we have discussed previously in connection with stellar evolution. I remind you, we have discussed an instability caused by the an instability of the stratification. And if you remember vaguely, then you will remember that this had to do with the gradient of the entropy. So the question is, how are these instabilities related? The instability we find here for n squared smaller than 0, and the instability we found once we considered the stability of the stratification of a stratification within a star. So we get to go back to the definition of the ends of the Brunt Vaisala frequency. It was defined as minus gravity times a quantity A. Well, if we relate the sign for stability or instability of n squared to the sign of A, because minus g is simply the gravity, we cannot change its sign, then this means the minus g means that we have stability in that case when A is smaller than 0, or instability if this quantity A is bigger than 0, or if alternatively, if we identify the quantity A with the gradient of the entropy, we have stability once the entropy increases in the star from the center to the surface. Once it decreases from the center to the surface, we have instability. Now, let us compare the quantity Q, whose sign was made responsible for stability or instability in our previous analysis, studying the stratification. Then we will find out, if we compare these quantities, that this quantity A is simply by a factor of 1 over rho identical with the quantity Q. That means the result of the stability or instability investigation is identical. We get the identical criterion for the onset of instability or for the prevailing stability from this consideration, from this local dispersion relation for gravity waves within a star, and our previous analysis where we in detail considered the stratification, the stability of the stratification. So the criteria are identical. Well, the quantities which enter here, which is the entropy gradient here, or this quantity A, are identical. So that means we are dealing with the same instability and the same physics. So we got to the same result. It would have been a disaster if we would not have arrived at the same result, but it's gratifying. We arrive at the same result, both with our previous stability considerations and with the local dispersion relation for gravity waves in our star. Okay, so we don't need to discuss this now in any detail, because it's exactly the same result, the same stability or instability criterion derived before. It's the same physics, and the discussion of this instability, of course, remains the same. Well, the quantity A in detail is now given by 1 over rho density gradient minus 1 over sound speed squared times the pressure gradient. Perhaps you remember this bracketed term and its relation to the onset of a convective instability, or if the sound speed goes to infinity, well, then this term will drop out, and only the density gradient will be responsible for stability or instability. We have stability then for decreasing density with height or with going towards the surface of the star, and instability if the density increases. Well, this is the Rayleigh-Taylor criterion again. Well, we don't need to discuss it again. So this contains all those stratification instabilities like Rayleigh-Taylor instability with respect to convection, either expressed in terms of the Schwarzschild criterion if we do not allow for the change of chemical composition, or we end up with Ledoux criterion if we admit a stratification of chemical composition. So everything is the same, and the discussion which we did previously remains valid and can be directly transferred to this case as well. Okay, so if we rewrite now the criterion in terms of the density of the pressure and the temperature gradient rather than in terms of the density and the pressure, then this quantity A is written in terms of the difference between nabla and lambda adiabatic, and then we obtain Schwarzschild criterion for the onset of convection. I'm not sure where the mouse has gone. Here we are, but it doesn't move. Okay, go a little bit down. Oops, it's too much. Okay, then we arrive at Schwarzschild criterion, which says stability if nabla is smaller than nabla adiabatic, and instability if nabla is bigger than nabla adiabatic. And similarly, we can derive Ledoux criterion by assuming for the equation of state that the density does also depend on the chemical composition. We have extensively discussed in connection with stellar evolution that one is not free to choose one of these criteria, but which criterion has to be chosen depends on the particular situation, depends on the properties of matter in our star or in the situation which you want to apply this stratification stability criterion. Okay, so we have both on both ways, both in the stellar evolution and here considering gravity waves, we have arrived at the same stability or instability criterion. Okay. Now, well, we now consider this dispersion relation in the opposite way, rather than considering it as a function for the wave number depending on the frequency. We now solve this equation for the frequency and as depending on the wave number. Well, let's go back and let's have a look what the dispersion relation looks like originally. Well, we have the sigma squared term here, and we have the 1 over sigma squared term here. So it's a fourth order equation in sigma squared. So we have to solve at least a quadratic equation for sigma squared. And to do this, once we do this, we end up with the following solution. Now, the sigma is now considered as a function of the wave number k. Okay, so we arrive at the quadratic equation for sigma squared, which has the solution given here. There is two bracketed terms which are identical here. They contain the Lamb frequency, the Brunt Vaisala frequency, and the radial wave number k squared and the sound speed, both here, and contain the Lamb frequency and the Brunt Vaisala frequency here. So these are the two solutions of the fourth order equation for sigma squared. Okay, is that better? Okay, thank you. Thanks. Well, to give it a more convenient form, let's consider large wave numbers, so large values of both the harmonic degree and the radial wave number. Then if we do this, then we expand the root appearing here. So if we take large values of k, large values of L and k, then this means the SL becomes large and the k squared becomes large. So this root might be expanded, and we are left with two branches, one plus minus this expression here, and these two branches are given in detail by the following expression. So sigma plus is simply the bracketed term, and sigma minus squared, the lower sign, is SL squared over n squared divided by the bracket. Okay, this bracket can be expanded for large values of wave number L and K. The bracketed term is given simply by the wave number squared, the total wave number squared, times the sound speed squared. So what do we obtain finally for the modes here? Sigma plus squared times 4 pi g rho bar oops. Okay, we got these two solutions. The sigma plus squared is given by wave number squared times sound speed squared. This is simply the spectrum, or is the dispersion relation for the sound waves, which we obtained previously simply by throwing out our G modes. And the second, the sigma minus squared, are given by the Brunt Vaisala frequency times the ratio of the wave numbers. It's also identical with the gravity waves we have found before by throwing out the sound waves. And these are the gravity waves, or the G modes. These are the sound waves, or the P modes. So they are contained all in this dispersion relation, and we find them as the two different solutions of the two different kinds of solutions of the local dispersion relation. Again, we see that the gravity waves, the sign of omega squared of the gravity wave is controlled by the sign of n squared, or by the sign of the entropy gradient. So if the entropy gradient is negative, then we have instability. The omega squared of the G modes becomes negative, and we have so-called G minus mode. We distinguish between G plus mode and G minus mode. G minus modes are those modes which appear once n squared is negative, or once we have a convectively unstable situation. The G plus modes are those modes which appear, or which are the solution of the system once n squared is positive and we have a convectively stable region. So G minus modes occur in convectively unstable region, and the G plus modes are the modes which appear in the convectively stable region. The G minus modes have with respect to time an exponential behavior, and the G plus modes have an oscillator with respect to time, not with respect to space. With respect to time, they have an oscillatory behavior. We have to distinguish between oscillatory behavior in time and oscillatory or evanescent behavior with respect to radius. This is not identical. Okay. So, next step. Once we consider the run of the frequency with wave numbers, then we observe, of course, what we already know. For the P modes, if K and L, if the wave numbers increase, the frequency increases, and the accumulation point of the P modes is infinity. So they start at a lower boundary, at a minimum. We have a minimum frequency for the P modes, and once the wave numbers increase, then they accumulate at infinity. L equals 0 is also possible here as a value for the azimuthal wave numbers. This corresponds then to the radial pulsations. Well, for the G modes we have the opposite. the G modes have an upper limit to the frequency, and if the wave number goes up, then the frequencies of the G modes approach zero. So the accumulation point for the G modes with infinitely high wave numbers is zero. The origin is the same as the convective instability or the stratification. The origin of the stratification instability, its buoyancy. Buoyancy is characterized by gravity and the entropy gradient, or the density gradient together with the pressure gradient. So the origin of these G modes, both the G modes and the convective instability, is buoyancy together with gravity. The necessary conditions or necessary ingredients for these modes is gravity and an entropy gradient. So if you don't have an entropy gradient, you will lose the G modes, and if you have no gravity, you will as well lose the G modes. Okay, if n squared is zero entropy gradient, you have no gravity waves. Well, with L equals 0, you have no radial G modes, and of course, for L equals 0, also the frequency of your G modes will vanish. If L is equal to 0, all the G modes are gone. We do not have spherically symmetric G modes. We know because buoyancy needs, for buoyancy to act, we need a perturbation of surfaces of constant density and pressure, and only then buoyancy can act. Therefore, we don't have spherically symmetric G modes. Okay, I already mentioned this. If n squared is bigger than 0, then omega squared is bigger than 0. We have oscillating, with respect to time, oscillating G modes. These are called the G plus modes. If n squared is smaller than 0, convectively unstable region, then omega squared is smaller than 0. These are the G minus modes, which have an exponential behavior with respect to time, and they represent, so to say, the convective instability. Okay. Well, we are now going to consider propagation diagrams. What does it mean? Propagation diagrams are diagrams in which we distinguish between oscillatory and evanescent behavior. Now, keep separate oscillatory with respect to the spatial dependence, not with respect to the time dependence. So propagation diagrams means we determine those domains in the star where k squared is positive and negative. Positive means oscillatory region. Then we have the solution oscillates with respect to the spatial dependence, and evanescent means we have an exponential behavior where the functions decay exponentially, having no nodes within the considered domain. For this purpose, we rewrite the dispersion relation in the form solved by k squared. So k squared, the sign of k squared, determines whether we have an oscillatory or an evanescent behavior, and we write it in the original form, just a little bit rearranged. And we consider whether the dependence of any quantity, well, dependence on R of the quantity for prescribed sigma squared is either evanescent or oscillatory. In any case, it's of course written by E2 plus minus IKR, and it depends on whether K is real or K is imaginary. Again, to remind you, oscillatory means K squared bigger than 0, K squared smaller than 0, and K imaginary means an evanescent behavior. So we may ask ourselves, when do these modes behave oscillatory or evanescent? Well, we have to discuss for this purpose the sign of this quantity, the sign of k squared, which is given by the sign of these two bracketed terms, and of course with n squared. Now assuming first of all that n squared is positive, so we do not have a convectively unstable region, then the sign, the mutual sign of these two bracketed terms determine whether k squared is positive or negative. So we have oscillator behavior if either sigma, well, if either sigma squared is bigger than n squared, then this term is negative, and if sigma squared is bigger than L squared, then this is also negative. We have negative sign twice. So in that case, the sign of k squared is positive. So if either both these bracketed terms have negative sign or both of these terms have positive sign, and this is given either by sigma squared being bigger than both bigger than the Brunt Vaisala frequency and the Lamb frequency, or if sigma squared is both smaller than the Brunt Vaisala frequency and the Lamb frequency. So both in these cases, you have both bracketed terms have the same sign, and in this case, k squared is positive, and we have oscillatory region. If they differ in sign, we have negative value for k squared, and therefore we have evanescent behavior. So keep in mind, either sigma squared is bigger than both Brunt Vaisala frequency and Lamb frequency, or sigma squared is smaller than both Brunt Vaisala frequency and Lamb frequency. In that case, we have oscillatory behavior. In any other case, of course, which is left, then if sigma squared is bigger than n squared and smaller, at the same time smaller at Lamb frequency, and if sigma squared is smaller than n squared and at the same time bigger than Lamb frequency, then we have evanescent behavior. Okay, now how do these quantities n squared and the Brunt Vaisala frequency and the Lamb frequency look like within a star? To that, in order to see this, let's consider the definition. The definition of Lamb frequency is, well, let's go back. Sorry, just a second. Lamb frequency and, well, the Lamb frequency is essentially the sound speed squared, so it will be bigger, goes with over r squared, the Lamb frequency. So this is a monotonic function which it diverges like 1 over r squared, and it goes down to small values at the outer boundary. So it's a monotonically decreasing function within the star. At the center we have 1 over r squared, so it diverges, and also sound speed is big. If we go to the surface, then sound speed becomes small, so it's a monotonically decreasing function from inside to outside. What about n squared? Well, for the center of the star, the gravity goes to 0 because gm over r squared goes linearly with radius, and also the quantity A involves gradients of density and pressure. The density gradient is 0 in the center. We have a horizontal tangent in the center, and also for the pressure. So the n squared goes to 0 in the center, and at the surface, well, we have terms like 1 over the density and 1 over the pressure type. Well, the quantity A, well, gravity of course has a finite value at the surface, but A goes like, A is proportional to 1 over rho times the rho by the r plus minus 1 over c squared times the 1 over 1 over p times dp by dr. So the sound speed becomes small close to the surface, and also the pressure becomes small. So we expect high values for the Brunt Vaisala frequency at the outer boundary of the star. So this seems to be a more or less increasing monotonically. Actually, it's not monotonically. We will see this in a moment, but it increases from the center to the surface. So it is an increasing function, whereas Lamb frequency is a decreasing function. So let us see schematically how the run of the sound, or how the run of the Brunt Vaisala frequencies and the well, so SL is a monotonically decreasing function, and n squared goes to 0, close to the center, and the n squared goes increases towards the surface. In general, n squared, the Brunt Vaisala frequency, does not have monotonic behavior. Okay, now let's go and consider the run of these two functions in general. I cannot scroll down. Okay, to the next. I want to go to the next picture. Here we are. Okay, now here the frequency is plotted. Maybe I go a little bit down. Oops. Just to see the bottom boundary. That's fine, that's fine, that's fine. Okay, so here we have plotted the frequencies, frequency squared, as a function of position within the star. Here the Lamb frequency, which is a decreasing function as a function of radius, and the Brunt Vaisala frequency being 0 in the center and increasing towards the surface. So what we can distinguish between evanescent and oscillatory regions. Well, if we saw if the frequency is both above the Lamb frequency, means here, and above the Brunt Vaisala frequency, we have an oscillatory region. This is the hatched region here. If the frequency is both below the Brunt Vaisala frequency and below the Lamb frequency, we have again an oscillatory region, and in any other region we have evanescent behavior. Why is that important? Well, if you remember, in the very beginning of this lecture we have considered the pulsations of a star as standing waves within the star. Alternatively, we have taken the analog of the organ pipe. So we have taken or considered both in the organ pipe and in the star, the pulsations as standing waves. Once we would like to have standing waves, we need oscillatory behavior, because with evanescent or exponential behavior, we would not be able to generate a standing wave. Well, that means in this part of the star, or in this frequency position or frequency and radius domains, we do not have standing waves, or we cannot generate standing waves. So we need these regions in terms of frequency and radius to generate or to construct standing waves. So what we are doing now, we are doing the same as we do intuitively for an organ pipe. We fill in standing waves in our oscillatory region, so we can fit in waves or standing waves only between these boundaries in the oscillatory domain. Here we cannot fill in any wave. So we fill in some wave, for instance, we fill in a standing wave with one node, with two nodes, with three nodes. So then we will have to fill in here a mode with one node, two modes, three modes, four modes, and so on. So we fill in our oscillatory region, we can fill in waves with a certain number of nodes. And these are the standing waves, or the waves which we ultimately consider as our pulsation, pulsation spectrum, or our standing waves representing stellar pulsations. The same can be done also in this oscillatory region. We fill in here in the oscillatory region. We fill in one mode with one node with two nodes, three nodes, and so on. And obviously, these with increasing number of nodes, the frequency of these modes will decrease, and here with increasing number of nodes, the frequency will increase for these modes. Okay, so we need this oscillatory region to define or to construct standing waves, which we ultimately then consider as the pulsation of our star. So that's done in a schematic way here. Well, the diagram does not look that nice for a real star. For a real star, the real star, it does not look that nice. It's here. Next diagram is the diagram for. Now, can we go jump back? Just stop here. Okay, that's fine. So this is also the propagation diagram now for a real star. The Lamb frequency still has a more or less monotonic behavior, decreasing from the center to the surface, but the Lamb frequency does no longer have a monotonic behavior. It's a rather complicated curve. Well, it's close to zero for the center of the star, and it increases towards the surface of the star. But else, there is a complicated behavior of the Brunt Vaisala frequency in this star. What might this be due to? Why is n squared 0 here, or capped 0 at a finite radius? Well, it's convectively unstable. We have convection zones, and once convection is efficient in the center of the star, what is the stratification? How do we characterize the stratification in the case of efficient convection? Pardon? Yes, nabla is equal to nabla adiabatic, and what does it mean with respect to the entropy gradient? It is 0, so n squared is 0, and that's what happens here. We have an adiabatic convective core, and so n squared is 0. It cannot be represented in terms of the logarithm, so it's way down here. So we have a convection zone here, and here it seems seems to be some indication of a very thin, might be a thin convective zone here. Elsewhere we have n squared positive, so we have propagating region up here, and here we have a propagating region down there. So this is a real propagation diagram. Okay, so now let's go back and consider what we will. Can we go back again? Can we? Yes. It's 2 or 3 pages back. Yes, that's it. It's a little bit down. Okay. What I just tried to explain was we have standing waves only in oscillatory regions. The evanescent regions are forbidden, so to say, And the discrete spectrum can only be determined by the oscillatory region, because only there we can have the standing wave. What we are doing, we fit in, or that's what I wanted to describe, is we fit in consecutively modes of standing waves with increasing number of nodes. So we start for the for the sound waves with the lowest frequency, put in one node, then the next one would have two nodes, and so on. Oscillatory character, of course, means we have the character of a propagating wave. Now, well, let's recall the dispersion relation for pure P modes we obtained by putting the Brunt Vaisala frequency 0 in the general dispersion relation. This was given by k squared being proportional to omega squared minus the Lamb frequency squared. So we see for pure P mode, this means the pure P mode has to satisfy the condition for propagation, for k squared being positive, that the frequency is above the Brunt Vaisala is above the Lamb frequency, of course. That means those modes which are on the upper part, on the upper propagating region, these are the P mode. The oscillator is the P mode oscillatory regime. And similarly, those modes for which, well, if we take now the dispersion relation for the pure P modes, we found that for these modes to be propagating or to be oscillatory, the frequency has to be smaller than the Brunt Vaisala frequency. So for pure P modes, we have the oscillatory region below the Brunt Vaisala frequency. So the domain of oscillatory regions of the combined system, which is below at the bottom, we had two in the schematic diagram. We had two propagating regions. The upper one is the P mode propagation region, and the bottom one is, so to say, the G mode propagating region, because omega squared, once omega squared is bigger than the Lamb frequency, we have propagating character, otherwise evanescent character, and the opposite is true for the G modes. They are oscillatory for omega squared smaller than n squared and evanescent elsewhere. Okay, so we may associate G and P mode character according to which we have frequencies above the Lamb frequencies or below the Brunt Vaisala frequency. So in our picture shown before, the bottom part is the G mode oscillatory region, and the top part is the P mode oscillatory region. Now I would like to go a little bit down. Okay, now let us go to some real or to some more or less schematic propagation diagram. Well, then in the less ideal diagram or less schematic diagram, we have an overlapping of the G and P mode propagation domains. So if we go down, now it seems to work again. Let's go down and let's consider the propagation diagram of the polytrope with index n equal 4. The line shown here, this line is again the Lamb frequency, but the Brunt Vaisala frequency is now no longer a monotonic function. It has a maximum and minimum here. It starts at 0 at the center and ends up at high values close to the surface, but in between it has both a minimum and a maximum. That means, let's go a little bit down to, okay, so what we have, thanks. Okay, so this is again the relative radius, and this is the frequency squared, which is plotted here. Well, we have the domain where the frequencies are both below the Lamb frequencies, and the Brunt Vaisala frequency is just enclosed by these two lines. And the other, this is the G mode, so to say, the G mode propagation region, where the frequencies are both below Lamb frequency and Brunt Vaisala frequency. And there is another propagation region where the frequencies are above both the Lamb frequency and the Brunt Vaisala frequency. So now they are not well separated, but they overlap. That means there are frequencies, once we have a mode somewhere here, frequencies which have two propagation region, one in the G mode propagation region and one in the P mode propagation region. And they are separated by a very tiny evanescent zone here. The evanescent zone is very, very small here, but in this range, the modes are evanescent, so they become exponential here. But in these two parts, they are oscillatory, and they may have, if you have a mode here, they may have a propagating or oscillatory character. G mode oscillatory character on the left part, and a P mode oscillatory character on the right part. So in that case, they are not, the G and P modes are not well separated. So we may, for instance, start filling in a standing G waves up here at high frequency. We have only one node here, 2 modes, 3 modes, 4 modes, and so on. So we start here with filling in the nodes for the G modes, and we do the opposite here in the P mode regime. So we start here with mode P1, three nodes, P2 with 4 modes, again with 3 nodes, then 4 nodes, 5 nodes, and so on. And we fill the P mode oscillatory region then with consecutively with standing P modes. But what you see here, well, in the overlap regime, we cannot distinguish whether it's a G or P mode because it has oscillator character both in the G and the P mode regime. In this case, the modes have a mixed character, and actually, well, to remind you, an ordering scheme for these modes is anyway, in a strict mathematical sense, not possible. So to label all these modes with P1, P2, and so on is questionable because there is strictly mathematically no ordering scheme. To remind you, for the Sturm-Liouville problem, the number of nodes, once you see the number of nodes of the eigenfunction, then you can immediately derive the order of the eigenfunction. And as you see here, what is called a P1 mode has 3, or if you add also the node in the gravity mode regime, then you have 4 nodes. There's obviously no relation between the number of the nodes and the order of the mode seen here. So it's highly questionable. Nevertheless, people, just for convenience, label the modes with indices which they think is appropriate. But there is no natural and no strict mathematical possibility to classify and to order these modes. Okay, we can make the break.